We're in unit number 5. Title of the chapter is Work in Kinetic Energy. In this video, we're going to talk about how to calculate work. And so we've got an example, and this is actually a rather lengthy example. So let's start out by reading the beginning of this, and then we'll see how it works out. Alright, draw a free body diagram of someone dragging a 60 kilogram box 10 meters with a force of 200 newtons at an angle of 60 degrees with the floor when friction is 40 newtons. Label all forces. Alright, so the first thing is we got to draw a free body diagram. So here's our box. The two easy ones are weight. We know the weight is acting on the box. We know there's a normal force acting on the box. It looks like somebody's dragging this box, and they're dragging it at an angle. So this angle here is 60 degrees. And let's see, now they're dragging it with a force of 200 newtons. Now we're not going to use 200 right now, so we'll call that an applied force. That's an A right there. And then there's friction, so friction is going to oppose motion, so that's why it's to the left. So F of F is 40 newtons. And then how far is this going to be dragged? Looks like 10 meters, so we're going to go 10 meters down the way. So there's our free body diagram, and we have basically 4 forces, and we'll start with question or part A. So it says calculate the work done by the person on the box. So actually there's 2 ways of doing this. So we'll start off with the work equation. So F dot D, we know that F dot D is FD cosine theta. And then see, now this is the force. Okay, let's say it this way. If you want the work done by the person, you have to use the work or the force exerted by the person. You would never, if you want the work done by the person, you wouldn't use the force exerted by friction. So those two always have to match up. So if you want the work done by the person, you have to use the force exerted by the person, which is FA. So this is going to be FA d cosine theta. I'm showing all the little bitty steps here. So that's 200 newtons, and then this is 10 meters. And then A is the tricky part, and here's how I work through this with folks. In class, I'll have them use their arms, but I'll use pencils in this case. So I've got 2 pencils, and one pencil is going to represent the force exerted by the person, and the other is going to be the direction of the motion. So one is the direction of the force, and the other is the direction of the motion. So here's the direction of the force. So there's A, there's FA right there. So that's this arrow. Okay, so it's going in that direction. Let's do it that way. And then its movement is this way. Theta is always the angle between those 2 guys. Well, they tell us that that's 60 degrees. So this theta in here is going to be cosine of 60 degrees. So come over here and plot that in. So we're going to say 200 times 10 times cosine 60, and we have 1,000. So the work done by the person on the box is 1,000 joules. Now that's method number 1. There's a second method to this, and I'm going to start with this one. I'm going to say work is, okay, F dot D, we get that. Work is equal to FD cosine theta. Work is equal to, now here's where it becomes interesting. You could say, well, this force and this movement are not parallel. There's only a component of this force that's actually doing the work, and that would be this component right there. So you could say, let me first figure out what that component is. That'll be what my force is, and I'll use that in the equation. So let's do that up here. So this is going to be actually the adjacent side, so this becomes then F cosine theta. So that's going to be 200 newtons cosine 60 degrees. Plug that in, 200 cosine 60, and we get 100 newtons. So you could say, well, yeah, 200 newtons, but not all of that 200 newtons is doing work on the box, because some of that is perpendicular to the motion. Right here, I calculate how much of that force is actually doing work, and I calculated it to be 100 newtons. So I could put 100 newtons in there. And then distance, 10 meters. And then cosine. Now, Since you just figured out the component, then your angle is going to be a little bit different. So this 100 is not the 200 that we used over here. This 100 now is this guy. And the motion is in this direction. So what's the angle between those two pencils? Well, the angle between those two pencils would be 0. There is nothing. So we'll plug in cosine theta, or cosine 0. So if I punch this all in, so that's going to be 100 times 10 cosine 0, that gives us 1,000. And look at that. It should be 1,000. We should get 1,000 from this point, and we should get 1,000 from this method, and we should get 1,000 from this method. So both ways work. In my opinion, it's just easiest to do it this way, but that's just my opinion. All right, part B. Part B asks us to calculate the work done by gravity on the box. So we know that work is equal to F dot D. Work is equal to FD cosine theta. Work is equal to, all right, let's see here. Work done by gravity. Well, this is the force that's doing the work. Well, potential for doing work. That's the force that we want. So that's the force due by gravity, and then distance, and then cosine theta. Now, I'm going to shorten this up a little bit because I know what's going to happen. I'm not even going to plug a number in for those two. I'm just going to look at the angle. What's the angle on this? Well, let's see, the force is down because that's the weight, and the motion is sideways, and the angle between them is 90. And look what happens when the angle is 90. If I do cosine of 90, by the way, make sure everything's in degrees, I get 0. Well, 0 times any distance and times any force is going to be 0 joules. So there is no work done by gravity, and that makes sense because the force exerted by gravity and the motion are perpendicular, and we shouldn't get any work done by. That's what we were saying earlier in the previous video. So we have 0 joules right there. All right, the next one, work done by the ground on the box. So this is going to be W equals F dot D. W equals, that'll be the normal times D times cosine theta. And let's just look at the angle, because look what's going to happen here. So if I go back up here, the normal is going to be up, and the motion is sideways. The angle between them is 90. So cosine of 90 degrees is going to be 0 joules. And that kind of makes sense because the normal and the motion are perpendicular to one another, so there shouldn't be any work being done. All right, the work done by friction on the box. Work is equal to F dot D. This is going to be FD cosine theta. Work is equal to, all right, so this is the work done by friction. So back up to the diagram here. That was 40 newtons. Now, it might be tempting at this point. You say, oh, ooh. That's 40 newtons. That's to the left. And if it's to the left, it should be negative. And you got to remember, you got to be careful. Down here, this F had the vector arrow on it. And so, yeah, I would agree negative there. But remember, when we drop down and do this this step, as soon as we add the cosine, we drop those vector arrows and those become scalars. So then this force is not a vector, it's a scalar, and I don't have to worry about direction, so it's going to be positive value. So we've got to be really, really careful about our signs on these. All right, the distance is still 10 meters. Cosine, now let's do the angle. This is friction and movement. So friction is to the right, and the motion is to the left. I said that backwards. Friction is to the left, and motion is to the right. What's the angle between them? Well, the angle between them is going to be 180 degrees. So we got to plug in down below 180. So then we get 40 times 10 times, let's see here, cosine of 180, and look what happens here. I get a negative value. Let's talk about that for a moment. Why the negative? Well, if I go into my calculator, I just plug in plain cosine 180. I get a negative value. So the negative value came from the cosine of 180. But another question is, why is it negative? And why were these two guys positive? What made these guys positive and this guy negative? Well, let's go back up here a little bit. What is this force causing this box to do? This force is causing the box to speed up. And so we can say this. If the work done is positive, it causes the object to speed up. Its kinetic energy will go up. Look at this guy. The friction is actually trying to cause it to slow down. It's preventing it from moving. So if the work is negative, that means it slows it down. So those two concepts are going to be used extensively in these two key concept boxes. What do we mean by positive work? And what do we mean by negative work? So let's go through these. Based upon our discussion, does the sign of work indicate direction? And the answer is no. Let me illustrate. Just because this guy is negative, down below here, and this guy's positive, the positive doesn't mean that the work is to the right. This doesn't mean the work is to the left. It doesn't indicate direction because, remember, work is not a scalar. Work is not a vector. It's a scalar. So since it's a scalar, there's no direction with it. So that positive and that negative have to mean something else. And what it means is it causes the object either to speed up or causes it to slow down. Sometimes we'll say endothermic or exothermic. Endothermic means energy is going into the system. Exothermic means energy is leaving the system, causing it to slow down. So if we go back over here, based upon our discussion, does the sign of work indicate direction? The answer is no. If so, work must be a scalar. Work is positive when the force or a component of the force acts in the same direction as the displacement. And that's what happened earlier on the first part. Positive work indicates that the work done by force, if the force were working alone, causes the object to speed up. Therefore, the overall kinetic energy, because it's speeding up, the overall kinetic energy, my pencil is running out now. Come on, pencil. The overall kinetic energy of the object increases. And since the force caused the energy level to increase, the work done by the force is classified as endothermic. You may have come across that word in one of your chemistry classes. Enter. Energy is going into the system. All right, negative work. Work is negative when the force or a component of the force acts in the opposite direction. Negative work indicates that the work done by the force, if the force were working alone, causes the object to slow down. Therefore, the overall energy of the object decreases. And since the force caused the energy level to decrease, the work done by the force is classified as exothermic. All right, so work is a scalar. The sign of the work doesn't indicate direction. It indicates the direction of the motion of the energy. Or that was a bad way of saying it. Let's try that again. Work is a scalar. The sign of work does not indicate direction. It indicates what's happening with the energy. Is the work going into the system, or is it leaving the system? That's the best way of thinking about it. In the next, actually, I'm going to keep going. All right, so you can work through worksheet number 5.1. I'm going to keep going with this one. So calculate net work done in a box. So we just calculated the work done in a box individually. Now we're going to calculate the net work, and this one's easy to do. So we have work done by the person pulling it, no work done by gravity or the ground, and then negative 400 done by friction. So let's put all those together. So if we want the net work, that would be 1,000 because of the person, plus 0, plus 0, minus 400 joules. So this is the person. Let's see, this was, I think, gravity. This was the normal. And then this guy was friction. And that gives us 600 joules of work. So, based upon your answer, is the object speeding up or slowing down? No, it's got to be speeding up. And it's speeding up because there's more energy causing it to speed up than slow down. Remember, the positive is going to cause it to speed up. Negative is going to cause it to slow down. All right, then the last one, calculate the net force acting on the box. All right, so net force, net force, net force. All right, so let's redraw that free body diagram so we can see it. So we've got, I think we had what, 200 newtons at a 60-degree angle here. We had the normal force this way. We had the weight going this way, and I think when didn't we calculate the component of this? And I think it was 100 newtons, and then I think friction was 40 newtons like this. All right, now the object is not accelerating vertically. So if it's not accelerating vertically, then all the forces in the y direction cancel out. I don't have to worry about those. But it is accelerating. We just said it was speeding up right here. It is accelerating in the y direction. It's accelerating in the y direction because there's more force going to the right than there is to the left. As a matter of fact, that would give us the net force. So 100 newtons minus 40 newtons gives us 60 newtons. So there's the net force. All right, the next one. Kind of moving through these a little quicker. Calculate the net work done on the box from the net force. All right, so we're going to use net work equation. I'm sorry, the work equation. Now, if I want the net work done, then this has to be the net force. And the net force I calculated in the previous example, and that was 60 newtons. And it moves 10 meters times cosine. All right, now I got to think this through. If I go backwards to this diagram over here, which way is the net force? Which way is that 60? Well, I got 100 going this way, 40. So the net force is actually in this direction, to the right. And the motion is to the right. So what's the angle? Yeah, it's going to be 0. So I'm going to come up over here. So the angle between the net force and the displacement is 0 degrees. And if I plug all that into my calculator, I get 600. And that'd be 600 joules. Does that make sense? Well, yeah, how about this? If I go back to part E, net force or net work was 600 joules. So we calculated the net work in 2 different ways and got the same answer. And we should get the same answer. So good. All right, how does the net work you calculated in part E compare to the net work you calculated in part G? And they were the same. Okay, next part. If the object started from rest, how fast is it traveling after the first 10 meters of pulling? So how are you going to get this? Well, let's start out with the big 3, and let's see what we've got. We want how fast at the end, so that'll be this guy. We know it starts from rest, so that'll be 0. It travels 10 meters. My problem is I don't have its acceleration and I don't have its time. So I have to get acceleration from someplace. And to get acceleration, I'm going to use Newton's second law. I'm going to sum up the forces in the x direction. Remember there were 2 of them? There was the applied force in the x direction minus the force of friction. We already kind of figured that out already. So let's solve for A. So FAX, we figured that out. I think that was 100 newtons minus the friction was 40 divided by the mass. And did they give us 60 kilograms? I know that's what it should be. Yeah, 60 kilograms right here in the first part. Alright, so let's plug all that in. Let's see what we get. So we got 100 minus 40 divided by 60. Hey, works out nice. 1 meter per second squared. So there's this acceleration. Now, that's not the final answer, though. I thought it was. I want the final speed. So that's, ooh, hey, I got the acceleration. So I got 3 of the 5, so I can use the big 3. So I think I'm going to use this guy here. Alright, let's give you a second to catch up. We'll plug that into the calculator. Alright, so what do we got here? We've got square root 1 times 2 times 1 times 10. And that gives us 4.47 meters per second. And there's the speed, positive because we had it moving to the right in our diagram. Alright, the last bit. How long does it take the person to drag the box 10 meters? Well, that's that time right there. So that's just another big 3. So VF equals VO plus AT. Initial velocity is 0. And there it is. So it took, to go those 10 meters, it took 4.47 seconds. I'm trying to figure out if I want to do the last part of this. Alright, I think I'm going to stop here. And the next video will actually start us out on page 6 with example 3, and I think we'll eventually pick these parts up, but not at this time. So that's the end of this video. Next video, example number 3.